So the topic is least squares regression. Last week we covered some part of that. We started from the linear regression, and we also looked at the main principle behind the linear regression, which is the sum of the least squares of the residuals. We have to minimize this sum. So based on this principle, the formulae for the linear regressions can be established. So for example, the formula for the linear coefficients A0 and A1 is determined from this system of two equations. So if we solve this system of these two equations, then we get the values of A0 and A1 as this. So this is for the linear regression using the approach of sum of the least squares of sum of the least squares of the residuals. Next, and then we looked at the example for this linear regression. Okay, so this example has been covered. Then we looked at the residuals and tried to understand the meaning of the residuals. And then we looked at the a measure which is called as the goodness of fit, which is determined as R square and R. R square is the coefficient of determination that determines how many percentage of points in the curve which has been established have been determined with certainty, or how much uncertainty we have removed. So closer this value is 1, better the results. So we did that example for the goodness of fit, estimation of errors for the least squares fit. So this we covered in the last one. And then we started about the non-linear curve fitting. But to start with, for the non-linear curve fitting, there are some types of curves which can be linearized. Okay, so for example, exponential, power, and the growth curves. Okay, for example, these form of curves. So for the exponential curve, for this curve, we take a semi-log. That means we take the log of y, and then we plot it against x, then that curve becomes linear. For the power curve, we take double log to the base of 10, and then that curve then becomes linear. And for this case, we take the reciprocal of both sides. Okay, so when we have the independent variable in the numerator as well as in the denominator, this x is in the numerator and x is also in the denominator, and then added with some constant, and then the whole fraction is multiplied by some constant. So in that case, we can take the reciprocal of that, and we can plot the reciprocals, that is y over y, 1 over y, and 1 over x. And then that will result into a straight line. So this is called as the linearization of the non-linear relationships. So let's look at one example of this linearization of the non-linear relationships. Suppose we have this data, x and y, an experimental study results into this data. So we want to fit this data into some relationship. Although in practice we have to judge that relationship by ourselves. Okay, here, but here it says that try to fit this data to this relationships. Y is equal to alpha 2 x beta 2. Alpha 2 x beta 2. That means try to fit this data into a power series. So if we want to fit this data into the power series, we have to take the log of the base 10 for both x and y. And then we can do the linear regression between these 2 points. So this we can uh, do it. So in the next figure is a plot of the original data in its untransformed state. And in this figure B, it shows the plot of the transformed state. So a linear regression of the log transformed data yields the result. So here you can see that in the untransformed case, X and Y, the plot look like this. In the transformed state, when we plot the log of X versus log of Y, then it results into this straight line. So for this straight line, the y-intercept is minus 0.3, and the slope of this line is 1.75. So since in alpha and beta represents the intercept and the slope, so in the power form, this expression will be y is equal to 0.5 x to the power 1.75. So this data will represent this power series. So let's see whether we get the same results in our Excel. In Excel, what we can do is I can take these data points. I already have done it, but I redo it again. So can you see the Excel here? Can you see? Can you see it?
Yes.
Okay. So we take log of X, we take log of Y. Okay, this is not the natural log, this is the log to the base 10. So we will use log 10. Okay, log 10 of 1. And then we take a log of everything. Okay, first we plot X versus Y, insert charts, and then I use this curve. So for example, this one. Yeah, this is the plot of X versus Y. So this is a non-linear curve. So let me just make it a little bit longer because to show the scale on both sides as seen. Okay, so maybe like that. So maybe like that. Okay, yeah. So now it's almost on the same scale. And then format the axis. I start this from 1, minimum 1. Okay, minimum 1. Yeah. So yeah, this is the, you can see now that this is like a non-linear. So at 1 it was 0.1 0.5. So here you can see that this is a non-linear curve. Okay, so maybe I can just make it more so that we have these as like squares. Yeah, so it's 6 and 6. Okay, so maybe format axis, and then on the x-axis boundaries are here, maximum is 6, units are 1, and then you can. Yeah, so this looks like this. So this is the non-linear graph over here. So if it is not a straight line. However, if we plot a graph between log x and log y, insert uh, chart. Where is this chart? Yeah, insert chart. Yeah, this one. Insert chart, and then maybe we can plot this one, this line. So here you can see that it's almost perfectly looking like a straight line. Okay, and then maybe we can just show it as a show it as a points only, and then you can see that the points are looking like this. So the distance between the first and the second point is large because we are now representing it on the log scale. But these points are now in the straight line. And then you can see that its y-intercept is almost minus 0.3. And it's we can also find its slope as well. So we can add a trend line as well. And then that may be linear. And then we can show its equation and r square over here. Okay, so this is the trend line and its equation. Okay, so its r square is almost equal to 1, and then the slope was 1.75 and minus 0.3002. Of course, here we have used directly the Excel to find these values of A0 and A1. But if we don't use it, then we have to adopt this same procedure which we have done before. Okay, in example 7. The first example. So we calculated the xy values. We calculated the sum of x, sum of y, sum of xy, sum of x square. Okay, and then we used these values for the formula of A0 and A1. Okay, this formula, and then we find the values of A0 and A1. But here in this, we have directly used Excel to find the same values. So, and here you can see that now, originally this was a power term, okay? And now let's see how close is that power term with this, okay? So for this, I think what we can do is we will determine that it is y is equal to alpha, okay, times x power beta, right? This is the formula. Y is equal to alpha times x power beta. So it is equal to alpha. What is alpha? Alpha is what? Is it 0.3 or 1.75? Alpha is 0. No, alpha is
17517.
1.75. Yes, it is. Alpha is 1.75. Let me see. Yeah, no, alpha is so log alpha 2 is minus 0.3. So alpha 2 is 0.3. So therefore alpha will be 0.5. We have to take the anti-log. Okay, let me do it over here. Anti-log, where is this anti-log? Excel. Okay, before calculating it, what we have found is we have found log of alpha, which is the y-intercept. Say C again, okay. Log of y. So the intercept, which is called log of alpha, okay, intercept is log of alpha. So log of alpha is the y-intercept. So it is equal to minus 0.3002. Okay, so therefore alpha will be equal to anti log. Anti-log. So do you know any the formula to calculate the anti-log in Excel? Anti-log.
Sorry.
This is.
Can you just do it like 10 to the power?
Okay, so that will be the 10 to the power. Okay, yeah. So yeah, we can simply write it as 10 to the power. Okay, 10 to the power minus 0.3. So it will be 0.5. Yeah. So this will be the value. Okay, and then the beta is directly this one. Beta is this because this is no, this is log of beta, not this is the log term. Okay, so log of beta is 1.7517. Okay, so that is the log of beta. Let me see if I am not making a mistake. No, I'm making a mistake. It is beta actually, not log of beta. Yeah, because this is the slope. Okay, so it is not. So we don't have to take the power of this. So that means it is not beta. It is not log beta. It is beta. Okay. So now we can calculate y is equal to this. So y is equal to alpha. So alpha is this value, and then f4. Make it as it will not change times x power beta. Beta is this value. Okay, f4, and then enter. So it will be 0.1875, and then like this. So it is 1.76, 4.27. It seems that the fit is not very well. Am I making some mistake? Is there any mistake over here? Let's see. Because the fit is not very well. Y is equal to 0.5 x power 1.75. It is 0.5. So yeah, I think I made a mistake. I put some wrong value over here. Is it? Let me see. No. 0.5 times. Yes, I took this wrong. I selected this value. I should select the value of x. So I should change to, instead of B2, I should change to A2. So that's why I was wondering what's happening over here. Yeah, now it's correct. So it is 0.5, it is 0.500. It is 1.7, it is 1.68. Okay. And then 3.4, 3.4, 5.7, 5.68, 8.4, 8.39. So it's very close. Okay. So here you can see that if we take the sum of the differences, so for example, the actual value minus the predicted value, and then square of that value, and then we add them together, and then maybe I'm making a mistake again. Okay, equal, these are the y values, this is the x y values, and then I take the squares, and then I get this. Okay, so you can see that the sum of squares are very small values. Okay, that is if I add it, this is the sum of the squares values. Okay, the sum of the square of the differences value. So which is very small. Okay, over here in this case. So that was this example. Okay. And similarly, we can calculate the R square or like that for this as well. So one more thing in Excel, okay, if for example, if I just change this data series for this original graph for the XY to these points only, and now I add the trend line over here, okay, I add the trend line. And in this case, I can select the trend line as not the exponential, it will be the power, okay, with power, okay. And then I show this equation over here. So I get the same equation. I will get the same equation. Here you can see 0.5, y is equal to 0.5009, the same, power x into x power 1.75, and with r square is always is approximately equal to 1. Okay. Similarly, maybe we can change also if, let's see, how about the exponential? But you can see that for the exponential, it is not fitting very well. You see, for the exponential, it is not fitting very well. And the R square is also low. If I change to linear, yeah, linear is looks a little bit better in this case. Yeah, it's because with the R square is 0.97 over here, but it is still not better than the power. So the power is like this, which is the same result which we have got from here. But in this case, what we have done is we have linearized it, okay, and then from the linearization relationship, we find the power relationships. Okay, so it's the same thing Excel probably is doing. So Excel maybe if we want to find the power relationships, Excel maybe linearize it first and then find the values for us. So maybe it may be using the same approach as we have done over here. So, okay, is it clear? Any questions?
No.
All right, so that's hard. So that was the linearization. And then next is the polynomial regression. Okay, so that it is the same as it is the same in the approach as the linear regression, but the instead of fitting a line, we will be fitting a curve. So some type of data fits very well with the curve instead of a line. So we can start it. We can start with the second order polynomial. So that second order polynomial can be represented as y is equal to a naught plus a1 plus a2 x square and plus e, which is denoted for some error. And if we take the value of the error, the value of the error or the residual square, so that will be given by this sum. And remember that the basic principle for this in these kind of regression methods is that we have to minimize this difference. Okay, but since in this case we have three unknowns, so we can, for the minimization, we have to take three partial derivatives. So after taking these partial derivatives and doing some algebra, we can rearrange the terms in this form. And then the solution of this system of three equations will give us the values of a0, a1, a2. And you can see that there is this pattern in the coefficients for these equations. So for example, the first value over here is the n, which is the number of points. And then is the sum of the x values, sum of the x square values. And then in the second equation, this starts from the sum of the x values, sum of the x square values. And then one new term is added, which is the sum of the x cube values. And then we have seen that the unknown variables are a0, a1, and a2. And then over here, the third line starts from the sum of the x square values plus sum of the x cube values, so which are repeated, and then one new term x sum of the x4 values are started. So it's easy to remember in this case. And on the right hand side, we have y, we have xy, and then x square y. So each time y is being multiplied by the power of x and then sum it. So very easy to remember this formula. So once we set up this system of three equations, we can solve these two equations, and then uh, we can find the value. So the standard error in this case can be found like this. So it will be SR over n minus m minus 1. Okay, SR is the standard deviation divided by n. SR is the standard error with respect to the standard deviation divided by n minus m plus 1. M is the degree of polynomial. So in this case, the degree of polynomial is 2. Okay, so it will be n minus 3 in this case. So this is the example for that. Okay, so suppose if we have the data points x and y, okay, and we want to fit these data points with the second order polynomial. So fit a second order polynomial to the data in the first two columns. Okay, so we have to fit the second order polynomial. So remember that for fitting the second order polynomial, we have to find n of course is the number of points. So number of points over here are 6, starting from 0 to 5. Okay, number of points are 6. And then find the value, sum of the x values. So we have to add these x values, we have to add y values, we have to take the square of x values and add them, we have to take the cube of x values and add them, we have to take the power, we have to raise the values of x to the power of 4 and add them. Then we have to multiply x and y values and add them. Then we have to multiply x square values and y and add them, and then we have to and that's all. Okay, so these are the things which we need. So m is equal to 2, m is the degree of the polynomial, n is equal to 6, which is the number of data points given. Uh, X bar is the average value of x that we will need for the error calculations. Y bar is the average value of the y. So for the calculation of the coefficients, we need the sum of the x values, the sum of the y values, sum of the x square values, sum of the x cube values, x4 values, sum, xy sum, and x square y sum. Okay, so all these values we can easily calculate. So for example, over here, over here maybe. So for example, here I have done the same example in the x1, xy, took the x square, x cube, x4, xy, x square, and then like that. And then once we calculate these values, so we have to rearrange in the form of this matrix. Okay, so this is the 3 by 3 matrix, and then this is the right hand side for the matrix. Okay, so this was the value of n. This is the sum of x values. Yeah, these are the sum of x values. So these are the sum terms. These are the sum terms. Okay, so sigma x. This is, what is this value? 55 is sigma. What is this 55 value? It is sigma. What? Are you following it?
Yeah, but
Sigma x square. Okay. And what is this 15 value? This is sigma.
the regular x.
Yeah, sigma x, and then sigma x square. And then what is this 225? This is
Cube, probably.
sigma x cube. Okay. and like that, okay? And then here sigma y, sigma xy, and sigma x square y. So we have this system of three 3x3 equations. So for solving it on Excel, I took the inverse of that. So you can see I took the inverse, and then I multiplied this inverse, this value inverse, with this column matrix, and then I got this final answer 2.47. Okay, so using this answer of 2.47, and then I calculated the estimated value of y using the equation. Uh, the equation will be, because this will be the coefficient of a naught. Okay, this will be the coefficient of a1. This will be the coefficient of a2. So the equation will be, yeah, this one, as I can show you over here. The equation will be this. Okay, a naught plus a1x plus a2x. Okay, a2x. X square. So plus a2x square. So using this equation, I find the estimated value of the y. Okay, estimated value of the y can be compared with the original value of y. So it is 2.1 and then 2.47, 7.7 and 6.769, 13.6 and then this. So here I can see that this value fits at a distance at a coefficient of determination of 0.9985 over here. Okay, so similarly we calculated the y minus y bar difference. So this is this one, but y minus y estimated square is only 3.74 over here. So this means that uh, the uh, the difference of this estimated values from the average is more compared with the distance of the difference of these values from the estimated value. As you can see that the sum of the squares of the residuals, sum of the squares of the residuals is only 3.74 compared with the sum of the squares with the average values. So this gives us the improvement for this R square value, which is 0.9985. So it is 0.9985 over here is calculated as like this. So it will be this value minus this value and then divided by 2513. So it will be 0.9985. So this shows that 99.85% of the points have been determined with certainty. Okay, in this case. So this is how it was then calculated, and then we can see that it was 0.9985, and the correlation coefficient is 0.999925. So here then you can calculate, and the standard error is calculated as like this, okay, which is 1.12. Okay, so that was the polynomial interpolation or polynomial regression. Okay, polynomial regression. Interpolation topic will come in the next lesson. After the polynomial regression, then we can look at the multiple linear regression. Okay, so remember that first we started from the linear regression, and then we did the polynomial regression, and in between we did the linearization of the nonlinear curves. Now we are talking about the multiple linear regression, which means that in this case we have instead of one independent variable, we have two independent variables. And since these two independent variables we can represent by x1 and x2, so their y value will not be a line. Their y value will be a plane. Okay, y value will be a plane. So by the same approach, okay, that is the using the sum of the square of the residual principle, we can formulate it. Okay, and the formulation for this becomes like this. Okay, so the formulation becomes like this. So in this case, we are taking two independent variables. So therefore, we will need to solve three equations. And then first we have the n values, the number of data points, x and x2 values, and then x and x1 square values, and then x1, x2 values. And here x2 values, x1, x2 values, and x2 square values. So here it is a little bit difficult to remember. So, but we have this formula over here. So sigma y, sigma xy, and then sigma x2 y. So basically, you can see that whatever the coefficients were before for x squared terms, those have been replaced by x2 terms over here. So in this way, you may be able to remember it. So earlier here it was x square over here. So then you can try to visualize. But anyway, I don't think I don't see much points in this case to remember this formula, because it may be a little bit different than in the arrangement than before. Or if there is any pattern, then maybe you can think about it to remember it, because previous formula had has a very good pattern. So you can see that n sigma x square, sigma x square, sigma x cube, like that. Okay, so that was formula. But in this formula, I don't see very well a pattern very well. So therefore, we have to use this formula. So in this case, in the multiple linear regression, the following data were calculated from the equation y is equal to 5 plus 4x1 minus 3x2. Okay, so we have this equation. So yeah, these equations we have. Okay, anyway, so but is just suppose that we have only these data points. So from these data points, can we get back this equation? So the answer is yes, we can use this multiple linear regression to get back this equation. Okay, so use multiple linear regression to fit these data. So for fitting these data, then we need to find these values. Okay, y x1 square, x2 square, x1 square, x2 square, x1 x2, x1y, and x2y. And then rearrange these values in this equation. Okay, so 6, 16.5, 16.5, 14 and 14, 48 and 40. And then here you can see that we are getting like a very symmetrical equation. So there is a pattern in this equation. Okay, so what is this? 6 is the n value, 76.25 is the x1 square value, and then 54 is the x2 square. So here we have the square values and the number of data points, and here we have the x1, x2. Okay, so x1, x2, and then 48 is the x square. So x square values comes over here. So there is some pattern over here in this case. So we get a symmetric matrix over here, and then we can solve it by the Gauss elimination or whatever method which you know. And then you can find that the value of A0 will be 5, the value of A1 will be 4, and the value of A2 will be minus 3, which are the same values from which we have derived these equations. Okay, so therefore it is useful that if we have the values of x1 and x2 and the corresponding value of the y, then we can find these, find the curve which can fit these data.
I have a question. So,
Yes.
but we cannot use this formula for this method for linear distributions, yeah?
Which formula? This formula?
Yes. When the multiple linear regression, we can use it only for the linear distributions.
Yes, yeah, it is for the linear regression. It is for the linear regression, but when we have more than one points, more than one independent variable.
Okay.
Okay, and lastly, in this topic, we have the non-linear regression. So up to now, we have talked about only about the linear regression. Okay. Even for the polynomial case, even for the polynomial case, so for example, over here, uh, here we have what we say the it is called as the polynomial regression. It is more like the uh, linear regression. It is similar to the linear regression. But for the non-linear case, when we don't have any polynomial, when we have something like exponential function, something like this, okay, exponential function, that means we have a data which is not fitting the polynomial very well, which is and which is not fitting the power series very well or line as very well. So we have to fit it to the exponential data. So for this exponential get function, we have to apply the non-linear regression. Okay, non-linear regression. So this non-linear regression has some specific uh, algorithm which needs to be followed. Okay, so let's the algorithm is given in the book, but I have not put it there in the slide. I have put only the example over here. So the example says that if you have the values of x and y like this, okay, and we have to fit it into this function a naught. That means you have to fit this function a naught into 1 minus e exponential function minus a1 power x e exponential function a1x to this data. So for this, we will use a method which is called as the Gauss-Newton method. And in this Gauss-Newton method, it will be an iterative method. So we need to find the values of a naught and a. So iteratively, we will start from a, the value of a naught as 1, the value of a1 as 1, okay? And then we will perform the iterations. So in those iterations, first of all, you will find the partial derivative of this function with respect to a naught, which will be this. Okay? And because it is with respect to a naught, so it will be a naught times 1 will be 1, and minus a naught times this, that will be e power minus a1 x. And then the partial derivative of x with respect to the second unknown, which is the a1, so partial f over partial a1. So it will be this value, a naught. If you will see, it will come out to be a naught x e power minus a1x. So if you will derive it, it will be like that. So you will take two partial derivatives. So after taking those partial derivatives, the next step is to find the values of these partial derivatives and arrange them into this matrix form. So we will get these values. So how we will get these values? So these values we will get from these equations. So we will take the value of x as 0.25. We will put it into this equation, and then we will find the value of partial f over partial a naught. So that will be the value of 0.2212. Okay, so then we will take the next value of x, which will be 0.75, and then put the value over here. So into this equation. And that will be the value of 0.5276. Okay, and similarly, we will put the values in this second equation, and then we will get the values in the second column. Okay, so this is how you will calculate a matrix which is called Z naught matrix. Okay, after that, the next step will be to take the transpose of this matrix Z naught. Okay, take the transpose of this matrix Z naught and then multiply it with the original matrix Z naught. Okay, so we will take the transpose of this. So we will put this transpose on the left hand side of Z naught, and then we will multiply this matrix, and then we will get this matrix. So 2.3193, and then this one. Okay, so after the matrix multiplication, we will get this matrix. Because you see that over here we have this 6 by 2, so we will get a 2 by 2 matrix. Okay, so this is the third
I have a
step. The
question.
next, yes.
Why do we transpose and multiply it back? What does this 4 by 4 matrix as a parameter mean to us?
We are following the algorithm of this Gauss-Newton method.
Okay.
We are following the steps of the Gauss-Newton method, and to refine, and the purpose is to refine these values of A0 and A1 so that it can fit very well. Okay.
Oh, okay.
So first step is this, and then we took the transpose and then multiplied it. And then because this will be, these coefficients will be the part of the equation for the answer. So we will need to inverse this matrix. So that means we will take this matrix and then we will find the inverse of this matrix. Okay. And then next step will be, we will find the vector D, which will be the consist of the difference between the measurements and the model predictions. Okay, so what will be that? We will take the we will put these values of A0 and A1 over here, which will be 1 and 1, and then we will find the value of the F over here. Whatever the value of the F we will find, we will take the difference from the given value of the Y. So in this case, that will be called as the matrix D. So it will be 0.28 minus 0.212. So because here we can see that it is 0.28, 0.57, 0. So these are the original given values. These are the original given values, and then we will subtract it from the predicted values. So these are the predicted values when we have the A0 is equal to 1 and A1 is equal to 1. So we will find this matrix over here. So we have this matrix over here. So after this, what we will need to do is we will need to take the transpose of this. We need to take the, we will need to multiply this matrix D with the transpose of this Z naught matrix. So the same Z naught matrix, its transpose, we have to multiply it with the D matrix. And then we will get this one. Okay. After this, then we will get this matrix, and then we have this inverse matrix. So we will multiply this inverse matrix with this as 2 by 1 matrix, and then that will give us the delta A matrix, that is the change in the A values, 0.27 and 0.512. So the new A0 and A1 values will be the initial A0 and A1 values plus the changes which we have calculated from here. So these will be the our new estimates of the A0 and A1. Okay. So these are the new estimates of A0 and A1. And then this process will be repeated. So after second or third trial, we will get the final result as A0 is equal to 0.79186 and A1 is equal to 1.6751. Okay. So this is a repetitive process, and then of course, which we this process we can do it on Excel as well. Here I have done it by myself before. So I put the X and Y values, then I calculated the values given by the function, and then here I calculated the square of the differences. Okay, so the square of the differences for the is 0.02. Then in the second trial, it is 0.02421. And then in the third trial, it has become very less. So here in this case, in the third trial, the values of A0 and A1 which were found are quite stable over here. So here and so in this first iteration, the values have been shown over here. So, and then what is this? Okay, so here I have calculated. So this is the this is the Z naught matrix. Okay, this is the Z naught matrix, and this is the transpose of the Z naught matrix. Okay, then I multiplied this transpose with this Z matrix, and the answer is here. And then I took the inverse of this matrix for of this green matrix. The answer is here. Okay, and here we have here I have the D matrix, which is the difference of this predicted value and the actual value. So this is the D matrix. This is the D matrix. Okay, this is the D matrix, and here I have what I have done is this is the multiplication of this transpose of Z matrix and the D matrix. So I have got this matrix, and now over here, what I have got is I have multiplied this inverse matrix with this. Okay, and then I got this delta A values. Okay, so this is delta A naught, and this is delta A1 matrix. And these were the initial values. So I added these initial values with the delta values. So then I got these new values of the A0 and A1. So these are the new A0 and A1 values. So these new values of A0 and A1 I will use in the next iteration, and then I will get the further new A0 and A1 values. So and then I will use it in the third iteration, and then I will get these values. And then when I can see that in the second and the third iteration, the difference is very small. So here you can stop your process, and then these will be the final A0 and A1 values for the model. So in this way, this process will work. So, and in fact, like I have also did it in the MATLAB as well. So I have wrote one script for that as well. Okay. So in this way, this process will work. Yes.
So when we want to fit for a certain set of data, doesn't it also mean that we should also know our initial predicted nonlinear function that we want to fit? Yes.
Yes. So we have to assume the form of our nonlinear function first, and then we will apply the partial derivatives based on that function.
Oh, okay.
So the form of this nonlinear function we have to assume by ourselves, and then we will fit this data into that function. Okay.
However, so will we learn in this course how to, I guess, guess the correct function for the fitting, or it is a topic for other higher courses?
No, I think by just with you, there is no separate learning for that. It is just by your experience. You will assume some function, and then you will try to fit it, and then that's it. Yeah. So there is no separate learning for that. Okay. So just by your own experience. Okay. So you will assume what function.
There were algorithm that could predict which kind of fitting would fit the model.
So once you will assume the function, and then you will apply the algorithm. That's it. Okay. So. And okay, I just want to remind you there is lab assignment number 2. So do you have any question about lab assignment number 2?
Currently, no.
Yeah, so this lab assignment number 2 has 4 questions. So in the first question, you have to develop the program in MATLAB for the Bairstow's algorithm. In the second one, you have to make some changes into the Gauss naive or Gauss pivot script, which is already provided. And in the third one, you have to illustrate the Cramer's rule in MATLAB. And in the fourth problem, it is a problem related with your structural engineering course. So you have to solve these 10 equations in MATLAB, okay, using the MATLAB command. So that is the lab assignment. So later on, if you have any questions, you are welcome to ask me. Okay, so yeah, today I have gone a little bit more than the time. That is fine. And